Okay, so now this would be a good point for me to go. And I want to tell you why I like deep learning, why I find the field to be very philosophically satisfying, and try to explain, give some not very widely known explanations for why it works as well as it does. So the thing about deep learning that makes it work well is that the hypothesis class. So in machine learning, when you want to learn something, you need to make some non-obvious prior assumptions about what your function should be. The prior assumption we make with deep learning is that you have a circuit. And circuits are a pretty good object to learn. So if you have a really deep circuit, it can do a lot of complicated computation. I think it is not a well-known fact that a modestly sized neural network that only has 2 hidden layers can sort n-bit numbers. So the hypothesis class is very powerful without requiring a lot of parameters at the same time. So the really amazing fact about deep learning, which is powering all the advances that we see, is that we can actually find those circuits automatically from data with gradient descent. It violates all theory. It exceeds gradient descent on these circuits exceeded all expectations. And it's an empirical fact, and it's really amazing. There is one other thing about deep learning which is interesting, where there is an argument by which we could have predicted that deep learning would have succeeded at least for perception. And the argument goes like this. If you look at, if you do a bit of introspection and we look at our vision and we look at our speech, you notice that we can see and we can hear things really fast. So you look at something in a fraction of a second, you know what that is. But our neurons are so slow, they fire at most 100 times per second and usually much less. Well, this suggests that the process of vision and speech and some expert perception, if you ask experts, experts often know what to do in complicated situations right away. This is a massively parallel process that doesn't require many steps. So kind of like a deep neural network, a very large deep neural network. And so, well, then what the question becomes, can we take the biggest neural network that we can? Can we get the biggest computer we can and train the biggest neural network that we can and see how well it's going to do? And it turns out that this works well enough to be useful for a lot of tasks. The other thing which is interesting about deep learning is that these models are so hard to understand. I think vision is a good example. I can speak for myself. When I was thinking, what kind of computer program could possibly solve vision? It was just an incomprehensible program. What kind of code, what kind of computer code could possibly do that? Well, if you assume that these perception problems are truly difficult to comprehend, and you notice that neural networks are truly difficult to comprehend, then it's actually pretty good. Because it's like fight fire with fire. It means that you found an incomprehensible solution to an incomprehensible problem. And I think we can make good analogies to evolution with natural selection. Just like with learning, we have a pretty good understanding in the process of learning. We can make certain statements about what the result will be. As we can with natural selection, biological evolution, we can predict that you'll have certain organisms, they'll be reproducing with high probability, they'll have, certain statements can be made, even though it's very hard to understand how biological organisms work. So I think this is a similar thing we're seeing here. And then there is a last thing which I want to highlight, which is really important, and that's compute. Compute has been the oxygen of deep learning. And if you think about it, it makes perfect sense. Let's go back to the early 90s when people are excited about neural nets and they say, yeah, we discovered backpropagation, we're going to solve everything. Well, but now your computer is so small, you can train a neural net with 40 neurons. It's not going to do much. No matter how good your machine learning algorithm is, no matter how smart the people who set it up, it's just not going to solve the problem. Success is not possible. And now, when computers are pretty fast, now we have a GPU, the new NVIDIA GPU can do 100 teraflop. Can you believe that? One GPU, 100 teraflop, that's pretty good. And now you can train big neural networks, and they can do more. And the reason that I feel a lot of excitement about the future is that even though Moore's law is dead, our laptops aren't getting much faster. Neural networks hardware is very much alive, and progress there is very rapid and exciting. And I expect that in the next few years, we'll see some truly unimaginably fast computers which in turn will allow to unimaginably to very exciting progress. So let's see, I have 2 more minutes. So I think in short, a lot of things are possible. The reason neural networks work are, A, because they're circuits, and finding the best circuit is a pretty good thing to do. And furthermore, we can look at human beings and look at the tasks they can solve in a fraction of a second, and from that make inferences about the kind of tasks big neural networks will be able to solve. Compute is really what's driving the whole thing, and more compute will result in better and more amazing applications. The one thing which I think I agree with some of the things that people raised is that the hypothesis class of neural nets, if you think about it as just a raw circuit, it's not the final hypothesis class. The final hypothesis class is programs. If you could find the best programs, then you're truly done. We cannot find the best programs yet, but hopefully we could maybe wrangle these models a little bit so that the results, so that the things they will produce will be a lot like a computer program in one way or another. So yeah, that's all I have to say. Thank you very much.
So it's always difficult to go the last, since my colleagues have already said basically almost everything I wanted to say. But I will try my best to keep you entertained before the break. So I just wanted to start by maybe reiterating into, we are talking about the breakthrough of neural nets, and it's actually quite interesting because, we are not really talking about a technical breakthrough here, right? It's not that suddenly we have amazing new algorithms that, we didn't have before. Right, there's been a few, algorithmic tricks that, have helped into making this, making training, better. But there is no fundamental change in the last, 25 years or more. So why are we, why are we here? Why are we talking about breakthrough of, I guess, deep learning, or now rebranded as AI, right? To the despair of people like Stuart. So, what came together was these algorithmic tricks, the availability of a lot of training data that was labeled, right, like ImageNet, for example, that Feifei developed. And as Ilya said, better hardware, right, that was actually making possible to actually train these models at a larger scale. And something that we shouldn't forget is actually also, the hard work of the grad students, right, like Alex and Ilya, right, that shown, really impressive results in computer vision, and then the field turned after that, right? So it's quite impressive that, that they were able to convince the whole community that we should pay attention to these models. So why are we talking about breakthroughs? I think that the real reason is that, these systems have enabled applications in domains that before, we didn't think about as, places where machine learning will make an impact, right? Whether it's health, whether it's transportation, whether it's, the most boring application you can think of, you see machine learning, AI, deep learning almost everywhere. And it's interesting. And as Mike was saying, sometimes you can, yes, build a model that can fake things, that is very good at faking, and actually, is okay if you don't rank your pages, exactly the perfect way. But you can get away with, doing a lot of things this way. Now I work in self-driving cars. This is a critical, safety application, right? So you can't fake things, right? You actually have to make sure that the system is robust and is not going to make, wrong decisions. And this is actually quite challenging for neural nets. For example, one of the issues is that they don't really model uncertainty well, right? So they will tell you, there is a car there, for example, with 99% probability, and they will tell you the same whether they're wrong or not, right? Most of the time, they're right? But when they are wrong, actually, this is a really real issue for, in this case, for example, self-driving, right? So you can't build a system that, has false positives, and you're going to start, just braking, in the highway at 120, kilometers per hour, whatever number of miles that is. So that's an issue that I think we should think about, and this also links to a better theoretical understanding of neural nets, right? So can we have confidence intervals of the error they're going to be making, and can we build systems that, again, they are robust based on this? I think that another thing that is interesting, and it hasn't been brought up by my colleagues, is whether now that we see a plethora of applications of, say, deep learning, is whether legislation is going to catch up with progress of technology, right? So, and self-driving cars is one of the examples of, are we ready to deploy these things? And will we be ready? And what do we have to change in order for that to benefit each one of us? Right? So I think it's something that we usually in an academic environment, we don't think about it, but I think it's, we are at the point where we have made so much, our technology has made so much impact in industry that we really need to think about that. Other things that I think are important, and Stuart mentioned this, is the fact that with neural nets or traditional neural nets, we're forgetting about modeling, we're forgetting about prior knowledge, we're forgetting about how can we encode the world in a way that actually is more interpretable, and again we are able to get confidence estimates about what we see. And perception is one of the canonical examples of this, where there is a lot of room to actually incorporate prior knowledge, incorporate good modeling, and at the same time learn these representations, because we don't have good abstractions of pixels, for example. Right? So looking at things like graphical models and neural nets and how these things can tie together, I think is a very, very interesting direction for the community. Something I also wanted to bring up is the fact that as there is more and more people actually using deep learning, we should think about education, right? We should think about, are people aware of the underpinnings of the technology they are using, right? So one canonical example is fairness, right? So when people use, our models on the cloud or whatever to, with their own data to train systems, do they understand that the systems can actually have biases? And as we deploy this in applications that matter for our everyday lives, are they understanding that perhaps they're going to make decisions that are not fair, that are going to impact certain sectors of the population, perhaps not in the right way. So I think that's something that, as educators, we should be really thinking about, how we make sure that people understand what these models can do, cannot do, and what potential caveats of the models are. And I just wanted to, finish with a positive thought, right? I said a lot of negative things, which is, where, for me, the future of deep learning, I think, I want to just talk about a little bit on applications and, self-driving cars being just one really, really exciting area. But transportation is just the first thing, towards really getting smarter cities, right? Our cities are growing, they're getting much bigger, and there is, a lot of issues that come with this, and I think that machine learning can really help for us to have a much better life. And when we think about this, right, so self-driving cars, for example, can, can save lives. There is, I think it's 1.2 million deaths per year in the roads in the world, right? That's a tremendously high number. We can reduce congestion, pollution. Studies says that there is only 1/10 of the cars that will be needed, right? But we also need to think about that it's not about building technology. We should also think about is the way we use the technology, right? If each one of us is going to just use a self-driving car individually, we are not going to help our planet, right? This is not the way to go. We should think of, public transportation, car sharing, ride sharing, and the same. And it's not just about transportation, right? It's about everything that we have, right? Our planet has limited resources. And we should think about how new technology can help us to make the world a place where everybody is equal. Thanks.
So I'll start our discussion by trying to summarize what I got from the panel so far. I'm glad to see that the people who are deeply involved in deep learning are aware of the limitations of these techniques, and they characterize it as it's a tool. It's a tool. It's not AI, not a human-level AI. It is a tool to be used in the context of other tools. But as a part-time theoretician, I would like to ask for a more clearer definition of the boundaries. If you are aware, if you can tell us more about the definition of the boundaries of capabilities of machine learning. Am I right in assuming that the boundary that I outline here, namely going from distribution to interventional questions, going to counterfactual. Is that the boundary that you are worried about? Or is there something more than that? In my simple-minded mind, I view machine learning as a tool to get me from samples to distribution.
So
And then we still have 2 more steps to go from joint distribution function, right, into real intelligence. 2 big steps. One is experimentation, and the third one is counterfactual. Am I right in segmenting the world that way? Or it has nothing to do with the thing that you are worried about? That is my question.
So I think the whole big problem is decision-making under uncertainty. And finding a mapping from A to B is just one little part of that. So, yes, you have to worry about counterfactuals and what might be. You have to think about rollouts of what's not really working and what might be working. There's a whole system you have to build when you think about it. You have to think about the economic issues. So, it's kind of things I find exciting with all the data around we can create new markets to link producers and consumers. So one I'm kind of involved right now is music, that there's tons of people who love to listen to music and tons of people who like to make it, and no one's making money off of it. Well, there's all this data. We can bring them together and let each musician know who likes them and create all these things. So that's a huge computation meets data analysis, meets prediction, and then many decisions being made in parallel. And then whenever you're making decisions, you have to think about the causal side. Because if you wiggle something and it doesn't give an effect, you can't actually do an action. You can't have control over the environment. So why would everyone separate out? The learning part is over here, and there's a boundary around that, and the decision part's over here, and the counterfactuals is over here, and the Monte Carlo testing out multiple alternatives is over here. It's all part of an integrated systems way of thinking.
And I also want to just point out, one of the fascination to me, but challenges of working in AI is actually, we as a civilization has very little understanding of cognition and like what human cognition is. And that's actually a really important sister field of AI. And because of that, we are, in a way, we're inspiring each other and learning from each other, but both at the very beginning. So when you talk about the boundaries, we don't even know the clear definition of what human cognition is, human intelligence.
But it's much easier to build boundaries on artifacts, like deep learning. That's an artifact, or a neural net. That's something that we have created, so we can analyze it and come out with the boundaries. Are we there?
Maybe one remark to make is that neural nets use backpropagation, which is the chain rule of calculus, to go back and change all the parameters everywhere. That's non-modular. So it's an end-to-end kind of way of thinking. You get an error out here in some part of the system, and you percolate everything back and make little changes everywhere. That's kind of antithetical to computer science modularity and keeping things separate. So that's just a fact we have to face, is that these systems that give the highest performance are going to make a system that's not very modular, not easy to understand, and not very easy to diagnose with. And that doesn't mean that one's right or one's wrong. It's just that we're going to have to face that issue going forward. That performance and explainability are a bit in trade-off. And also just thinking how humans think about the world, we don't really separate off one part from the other. Things over here can influence things over here, and we're kind of happy with that. And so the keeping things simple in modules is something that we may have to sort of slowly release as part of systems that really learn from data and take into account all the possibilities out there.
So I have 2 things to say. First is about modularity, and second is about how to think about the limits and the progress in the field. I actually like the comment about modularity. I think there is a bit of a nuance there that the end systems that we learn usually tend to not be particularly modular. But now we have the ability we have these great blocks which we can compose together to create whatever neural net we want. Then we train it. And so it's really convenient that you can take any kind of data format that you want on the input side and almost any data format on the output side and set it all up, and the system is going to work. And what's interesting is that all these different applications, they're all driven by the same set of algorithmic constructs, by the same set of ideas. And what that means is that anytime anyone makes an advance, The advance goes at the level of the, often can go at the level of the algorithm, and that will expand the boundary of what is possible, not just in one application, but in all applications in general. And so it is true that some kind of boundaries exist right now. They are a little bit blurry, and they're still being pushed. And I think it's hard to tell how far we'll go just with the current set of ideas, excluding any new ones.
So I think it's instructive to look at AlphaGo. So everyone's very impressed by the fact that AlphaGo is now wiping the floor with every single human being on Earth. And it's often described as a deep learning system, but actually it isn't. It's a very classical system. It would be easily understandable by Arthur Samuel. It's essentially an improvement on Arthur Samuel's system from 1957. And it has several components, and the deep learned part of it is just one, well, I guess it's two of the components, but perhaps the core component still is the fact that AlphaGo knows the rules of Go, in the sense that for any given position, it knows what the legal moves are, and it knows what the next state will be when each of those legal moves is executed. So that's the causal theory, coming back to Yuja's point, the causal theory of the domain, and that's written by hand in C++, or something related to C++, right? It's not learned. The learning part of it probably wouldn't work. It includes transitive closure because the liveness of a Go piece depends on its connectivity to all other Go pieces, and so there's a transitive closure thing which is hard to do in a fixed depth circuit. So potentially you could learn the rules, again, by experimentation, but in fact they found it much easier to use a nice expressive programming language to write those rules, because as we know, the rules of Go are pretty much translation invariant across the board, and they're also time invariant. And so there's that. And then there's the forward search, the exploration of future possibilities, which again is a very classical idea going back at least to Aristotle and maybe earlier. And so this I think is emblematic of what we're going to see going forward, that the way we build systems is not just end-to-end. If you took seriously the idea of end-to-end deep learning of Go, you would have to learn a policy. Namely, you would take millions and millions of Go boards, you would take the move that was made by some expert program or by human Go masters, and you would train a policy that maps from boards to moves. But that is not how it works. That does not, as far as we know yet, work very well. People have tried that approach in backgammon, for example. It didn't work very well. It doesn't work for chess at all. And so it's this breakdown of the decision problem into its underlying elements, the transition model for the domain, the ability to look forward in time, and the modular knowledge of how to represent the transition model and what it does. Those elements, I think, are crucial, and they're not end-to-end learning.
Related to that, and what I was trying to introduce here, can AlphaGo take advice from a human being? You shouldn't have done that. You would have been better off had you taken this move. Would it be able to understand this kind of advice, or perhaps it needs a whole new architecture to be able to understand such advice? That's my question.
But it's not an architecture, it's a problem to be solved. So if you sat down and wrote AlphaGo as a program, as Stuart's talking about, you do a lot of Monte Carlo rollouts, you build a policy up, and you build a system that does that. Right now that's reinforcement learning is the underlying technology that does this. And it's a kind of dumb try things out, but then kind of smart engineering to make it not intractable. There's something called apprentice learning in reinforcement learning. It's another part of reinforcement learning where you take advice from a human. You watch a human doing it, and then you learn that. So it's all a big toolbox. It's not that you're building an architecture that can or can't do something. It's that you sit down as an engineer and you say, I want to make a helicopter fly, or I want to do a Go. And we're not building a single device that does all those things. That maybe in 500 years we'll do that. But right now what we got to develop is an engineering side of our discipline that thinks about how to build a system that does, here's the goals of the system, here's my guarantees, and here's how I build the system. And we're so far from that that, you know, we have to get real. We have to think of systems way of thinking and machine learning. To me, there's a lot of systems people in the audience, and I think that your way of thinking together with the mathematics of machine learning, that's the future.
So I agree with Stuart and Mike of what they've been talking about. I think that you know, we shouldn't just think of you know, deep learning as it's going to solve all our problems and it's going to learn anything whatsoever, right? So I mean, it has, you know, very high capacity, but still you need to be able to get to that solution, right? So for example, one can do a demo that works pretty well into how you input images and then you output the steering wheel. And that's fine for doing a demo, but that's not going to solve the end task of it has to work at every point in time. And when you make a mistake, you need to explain why you made that mistake. And this is why then you need to, again, interact with modeling, but at the same time, when you learn your neural net components, they should be aware of the whole system. And that's the interesting, difficult part on all this.
Unless you have other comments to make, we are going to open the floor for questions from the audience. Oh, no questions. So, okay.
Wow.
Yeah. Education was mentioned. What should we be teaching or learning ourselves to make the most significant advancements? What are we, what is supposed to understand or teach? Any comments on that?
So,
I have a comment. What do you teach in a neural network kind of class? It's related to the question.
Go ahead.
I'll just say one thing, and then Stuart, I just finished teaching the largest neural network class at Stanford, 770 students. We teach neural network. We teach calculus. We teach chain rule. We do Taylor expansion. We teach backpropagation. And then we...
what is not true about neural network?
What is what?
I'm saying not true because teaching is conveying information. Information is what cannot happen in the world. So tell me about neural network. What are we sure cannot happen in neural network? If I had another layer, it's not true that. Go ahead.
So one thing about this kind of statement is that this statement, so a neural network is a circuit of a certain limited size. And that question is related to the question of what can a circuit of a certain size not do? And those of us who are more on the theory side know that these questions can be extremely difficult to answer. And this is precisely why it is so hard to delineate precise boundaries of what can and cannot be done. And there's a lot of experimentation going on. And oftentimes, you think that something can't be done, and then later someone figures out that it can be done.
Yeah, so I'm rewriting the AI textbook right now to figure out, how do we incorporate deep learning. And we have a real problem because we have a vision chapter right now, and then Ian Goodfellow is writing the deep learning chapter, and I suspect the vision chapter is just going to say, see chapter 19. Right? And then we have a section on speech recognition. It's going to say, see chapter 19. So this worries me because then you don't really understand speech. If your approach to speech is get lots of speech data and train a deep learning system, and your approach to vision is get lots of vision data and train a deep learning system, I think that's really selling the student short on understanding the speech problem, how it connects with language, how speech is produced, the structure of sound, and then the same with vision. So I think we're really struggling to figure out how to retain the core content of these areas, even though the fact is that right now, by far the best speech recognition systems are end-to-end deep learning with really no internal structure. All the stuff that we used to teach about hidden Markov models and acoustic models and mixtures of Gaussians and all that stuff has gone by the wayside in practice. So
Wait,
that's a
Stuart,
problem.
I hope you have a good chapter writer for vision, because I think that's exactly what we do in the labs. We talk about what we cannot do in vision, right? Like the whole 3D vision understanding. You know, even in object, there is, because of ImageNet, a lot of people think we've solved vision. It's not true at all. We all know what are the open problems of vision. We don't understand we don't even understand objects themselves, the parts, the relationships, the affordances, how it can be manipulated, the texture, the transformation under all kind of variances. So I think this is so important in the days of deep learning, especially in the hype days of deep learning. We actually have that discussion and analysis.
Are you volunteering to Thank you.
So can I make one
Yeah, we
more
have a-
brief comment on, I just take an opportunity to say something about the curriculum in general, not just deep learning, but the CS curriculum I think needs to be revisited to have more statistical, and so I like to call it inferential thinking. The counterbalance to computational thinking is inferential thinking. If you're doing an A/B test in industry, which people do all the time, you're trying to think about what could happen next, what's behind the data. That's a form of inferential thinking. Error bars and confidence intervals are things that could happen but didn't happen, but you have to protect yourself for. And too few of our computer science ever see those concepts. So one way of doing what she's talking about is the cloud. You do things not just once, but you do it in parallel 100 times, and you can get an error bar. So there's a natural match to some of the ways we think in computer science to the needs of inferential thinking. And I think our CS curriculum just needs to be really revised from the bottom up to start introducing those concepts. You can go through a whole CS curriculum and see a little probability, but see really no inference. And I think that's really something we have to change. And that's what I teach when I teach things like neural nets. I say it's part of a bigger picture of statistical decision making and inference.
Yes, I think, just one more comment. I think it's very important that a neural net class should start by what is machine learning and what are neural nets in the context of machine learning. By making sure that everybody has a bigger perspective and it's not just deep learning, which is unfortunately what is happening in many, many places that they just forgot about the rest.
I want to apologize for my biased selection of the questions, which are affected by the legibility of the handwriting. Here is one that I could read. How and why should people trust a deeply learned system that makes a decision? How can they expect why should we trust recommendation made by deep learned system?
So that allows me to bring in another theme that I like to make, which is databases. So we can't divorce this style of machine learning thinking from database thinking. Database people, for example, talk about provenance of data. And I need to be able to track back where a data point came from before I'll trust an inference made by a box that was trained on that data. So in medical decision making, you have all the time that data was collected in some era, a learning or statistical system was built based on that, and then 10 years later, the inference system is still being used, even though the machines may have changed. So the data is actually out of date. And if we don't build systems that take that kind of provenance into account, so that you can say, you can trust this inference, not just because it's a deep learning system or whatever, but because it came from this place, and that makes your inference relevant, then you're not building an overall system that you can actually trust at all.
I think we should think about, humans are pretty, many times pretty bad at making decisions, and even worse at explaining why they make those decisions. So, we need to think about we are also extremely hard with machines, right? And we should keep them to the same standards.
And here's a question. Can you discuss the issue of mental modeling? I couldn't read the next. And if I ask, how do you fix a broken phone, you can answer it without breaking your phone. And anyone wants to comment on that? I mentioned that ability to be able to have a mental representation of the environment, and one of the greatest breakthrough in the computational capacity of Homo sapiens. So yes, if you have a causal representation of your environment, you should be able to manipulate it in your head before you do it physically. That is the great advantage of having a mental representation, and this is one element which I do not find in neural nets. So evidently that is something to work on. Another one is how, yeah. Oh, boy, missing here. Oh, there's one question here about the specialization of neural net. What we find today is machine learning today, the systems we find today are specialized. Do you think that pursuing a general purpose machine learning AI is really worth it? Unless you...
So I can say a few words on that.
I would say, is it feasible?
So special purpose versus more general purpose, it really depends on the problems that we're trying to solve. Many problems that we're trying to solve are indeed fairly specialized, and so for those problems we should use the most specialized approach possible. But as we set our sights towards more ambitious goals and more ambitious systems that can, let's say if you think of Let's think of an automated mathematician. I think a system like this will need to be quite a bit more general than a system which does something quite narrow. And so what will happen is that it's not quite feasible today, but as our computers will inevitably get much faster, I think these kind of systems will become, at least it will become possible to design systems which could credibly, you could imagine, if you just give it the right experiences, would do what you'd want.
Anyone else on the question of generalizability?
I think the way to approach it is to always play devil's advocate with yourself and say, okay, I built something that I think is more general than something else. Where does it break? So if you take, for example, DeepMind's DQN system, which is somewhat general, it learns to play a wide range of video games purely from the visual input provided by the game. And that's held up as one of the first examples of something that moves towards general purpose AI. And it's driving games, it's ping pong games, it's mazes, and all of it. If your baby learned to play those games at a superhuman level in 2 hours after birth, you'd be pretty terrified. But when you actually say, okay, well, does that technique generalize? Well, the number of time steps that the system is capable of handling in terms of the time scales of rewards, the time scales of realizing the benefits of actions and so on, it's in a few tens. When you think about, okay, now translate that to human physical action and the scales that we operate on, which can be deciding to go to a conference months in advance, the conference itself is hundreds of millions of physical actions. And we make decisions on the scale of billions or even trillions of physical actions. It doesn't possibly scale up to that. The approach does not work, it fails, it breaks. And then you have to say, okay, what could we do to get past that bottleneck? But there's not an infinite number of such bottlenecks. And we will pass through them eventually.